Okay, so just to recap our warm-up here, we found the slope of the tangent line, again, at x squared minus 4. And we had done this problem before. Let me flip back to our notes from, yep, here we go. Okay, so remember we established that what we'd have to do is make those two numbers very, very close to one another. Those 2 points, rather, very close to one another. Here was our visual for that. Okay, here's at 1. This is x squared minus 4. Okay, this is at 1. We were getting those 2 points as close to each other as we could. The closer those 2 points are to one another, the better approximation this is for a tangent line. But do we all see how no matter how close I get those 2 points, it's still not a tangent line? You guys get what I mean by that? No matter how close we get those 2 points together, it's still a secant line, not a tangent line. But it gives us an approximation, or I guess like an educated guess, for what the tangent line, the slope of the tangent line is roughly. Okay, so going through, and we used our calculator to get our table of values. Let's just flip back to Okay, this was our average rate of change. Again, that's what you guys came up with. Oh, and I wanted to also point out that this simplification part is completely optional. You do not have to do the simplification part. If you didn't, you would come to the exact same answer. Okay, so, but if you get to there, at least here, you don't really even need to use your calculator. You can if you want to, but you're just adding 1 to your x value. So, so again, we see that our average rate of change is approaching 2 as the interval gets shorter and shorter and shorter. So we can say in an educated guess that the slope of the tangent line is 2. So let me add to this also that then the equation of the tangent line is going to be y minus the y coordinate. Let's see, what was the y coordinate at 1? F of x was x squared minus 4. So f of 1 was a negative 3 equals the slope, which we saw was approaching 2, x minus the x coordinate, which is 1. So you can even just leave it like that if you want to. All right. Feeling okay about that? Okay, so that's going to be a good introduction to what we're going to be covering today. Let me write the section number that we're going to be covering, and then we'll dive right in. So this is section 2.2, and we are going to be talking about the limit of a function. And we aren't going to be using that handout just yet, so if you just want to put that off to the side, take notes like you normally would right now, and then we'll use that handout in just a little bit. So the limit of a function. This term might be slightly, it might be completely new to some of us, the idea of limit. So I don't know if this is true or not. This is the way I think of it. I think of the way the word limit comes from is, do you see how there's really no limit on how close x can get to 1? Right? I could add another 0 here, or I could add another 9 here. I could add 5,000 zeros here, and that's very, very close to 1, but it's still not 1. I could add 5,000 9s here. Again, we're very close, but could I add even more than that? Yeah, again, there's no limit to how close these numbers can get to 1. Okay, so the idea here is that with the previous example that we did, we were looking at the average rate of change of the function x squared minus 4 on the interval from 1 to x. Okay, and we found that that came to, I'm just going to go ahead and run through it again real fast because I want to make sure we're all clear on where this comes from. So f of x minus f of 1 over x minus 1. Okay, again, this represents the slope of the secant line starting at 1 and ending at x. So f of x is x squared minus 4. F of 1 is 1 squared minus 4. I also want to do this so I can point out some notation because I was going through the boards and I'm seeing some of the boards have horizontal equal signs. A good rule of thumb here is that you do not ever want to have more than one equal sign in a line of work. Okay, so I've got one equal sign, and I realize I'm out of room, so I couldn't go over here anyway, even if I wanted to. But I've got one equal sign. Now everything should flow vertically from this point. Okay, so this is what I also expect to see on lab write-ups, anything really. This is the notation I'm looking for. So minus negative 3. Okay, so again, we get to x squared minus 1 over x minus 1. Okay, so that means the average rate of change for this function on 1 to x, it can be given by this expression right here. Okay, so we found, using the table, and we can simplify this or not, but we found that as x approaches 1, x squared minus 1 over x minus 1 approaches 2. Okay. Now, one thing I want to point out here is we are approaching 1. Okay. What happens if I let x equal 1? I know I might sound like a broken record, but this is really important. I get this 0 divided by 0, right? If I let x actually be 1, I get 1 squared minus 1 over 1 minus 1, which is 0 over 0. So if x equals 1, x squared minus 1 over x minus 1 equals 0 over 0. And remember, this is what we call indeterminate form, because we can't determine what it is. Remember, the idea of it being indeterminate is it's like saying 0 times what equals 0. What can I multiply by 0 and get 0? Absolutely anything. Okay, so it's indeterminate. All right, so this is saying not at x equals 1, but as x gets closer and closer to 1, this thing gets closer and closer to 2. We don't care what's happening exactly at 1. So this is the idea of limits, is that we want our input to get as close to a number as we can possibly get to. And again, there's no limit on how close we can get to that number. And we want to see what this expression approaches, what the y value of that expression approaches. So rather than using this notation, we are going to use what we call limit notation. So let's talk about that. Limit notation. So right now we're kind of taking a step away from the idea of tangent lines, because we need to kind of build some tools in our tool belt here to better understand and better compute slopes of tangent lines. So we need to understand limits a little bit more, this concept of 0 over 0 and the idea of approaching. So with limit notation, the way that we are going to write this is LIM, limit. Underneath the limit, we are going to write what the input is approaching. So x approaches, I'm going to do this one here. So x approaches 1. Then next to that, you're going to write the expression that you want that input to be, approaching that number. So the expression that we were looking at was x squared minus 1 over x minus 1. Okay, so we would say that this limit, based on the table that we had, equals 2. So this says the same thing as this. It's just that this is more condensed, and it's going to offer a lot more versatility for us to have this notation instead. But it still says the same thing. So the way that we would actually read this out loud is the limit as x approaches 1 of x squared minus 1 over x minus 1 is 2. That's how we would read that out loud. Another way you could read it, if you wanted to, is you could say the limit of x squared minus 1 over x minus 1 as x approaches 1 is 2. So you can kind of reverse the order a little bit. This is the way I tend to do it, because it kind of follows the left to right reading path. So the limit as x approaches 1 of that expression is 2. Okay, so that's the notation that we're going to use as we go through and talk about limits a little bit more. The main limits that we're going to be talking about, and we're not going to do it just yet, but we're going to be wanting to look into this 0 over 0 situation a little bit more. And the reason is because any time I find the equation, or if I want to find the slope of a tangent line, I will always get this issue of having a 0 divided by 0. Let me tell you what I mean by that. So, for example, like if I had some function, I'm just going to do a general graph here. Let's say this is f of x. All right, if I wanted to find the slope of the tangent line at some point A, okay, I'm going to freehand this one, but I recommend rulers anytime you're doing a tangent line. Do we all agree that that's tangent to the curve? Yes? Okay. So again, remember the issue and the beauty of a tangent line is that it goes through one single point. In order to find the slope of a line, we need it to go through 2 points. So what we've been doing is picking another point that we've been calling x. We've been finding the slope of the secant line between those 2 points. And then what have we been doing with x? You got it. We've been bringing it closer and closer to A, right? So I drew it over here just for visual purposes, but we've been trying to bring it in and get it closer and closer to A. Can I also put my x point over here and bring it in from the other side? Absolutely. That's what you guys have done on these whiteboards. You guys all have like a 0.9, 0.99, and a 1.01, 1.1, right? We've gone from both sides here. So notice this point is coming in from the left side. This point is coming in from the right side. We're going to be using that terminology a little bit later on. So the idea here is that in order to find the slope of the secant line, what I have here is I need my change in outputs over change in inputs, right? So this is going to be f of a, whatever that is. This is going to be f of x. So the rise over the run, the rise is the change in my y values. The run is the change in the x values. So right now what I've written is the slope of the secant line on the interval from a until x. In order to make this a tangent line, we want that x point to get closer and closer to the a point. We have new notation for that. So I can write the limit as x approaches a of this thing is going to give us our slope of the tangent line. I'm going to go ahead and write that as m sub tan. That's the slope of the tangent line. I think your book uses this notation. And just for clarification, let me write f of x minus f of a over x minus a is your slope of the secant line. So basically, just the change in y over change in x is your slope of the secant line. It's when you then take a limit and get those 2 points as close to each other as you can, that then becomes the slope of the tangent line. And this is the notation we can use for that. Okay, but we need to explore this a little bit more. Because do you guys all see how if I were to just let x equal a in our m tangent equation, I would get 0 over 0 every time. No matter what a is, no matter what the f function is, I will always get this 0 over 0 situation. Okay, so we'll be exploring that indeterminate form a little bit more. Okay, so let's talk about limits. There's basically going to be 3 ways that we're going to evaluate limits. And when I'm saying evaluate a limit, what I mean is we're going to have like the limit as x approaches a of some function. This function does not relate to this function up here. This is kind of referring to why limits are important, and then now I'm talking about just the general notation of limits. So if we want to evaluate a limit, it's going to look something like this, where f of x is going to be some expression, and a is going to be some number, just like this right here. If we want to evaluate that limit, one thing that we can do is we can evaluate it numerically. And what I mean by numerically is that we plug in numbers that are close to that number that we're trying to approach, right? So in this case, we are trying to approach 1, so we plugged in 0.9, 0.99, 1.1, 1.01, very close to that. So basically, we're making a table. Another way we can evaluate a limit is graphically. Okay, using a graph. Slightly redundant. The Department of Redundancy department. You guys heard that? So you can also look at the graph of the function and look at what's happening near a. Okay, and then we can also look at this symbolically, which means we're really using algebra or limit laws, which we'll talk about. Okay, so we've kind of already investigated numerically quite a bit, because that's how we've been finding these slopes of tangent lines, is looking at these expressions, these average rate of change expressions, numerically. Let's take a look at how we would do that graphically. So let's do some examples. This will be example 1. I'll just say, thank you, evaluate. Right now, we're just going to go ahead and start with numerically and graphically. I'll do capital A, I guess, for example A. Okay, so let's go ahead and start with the limit as x approaches 1 of x squared minus 1 over x minus 1. Now, I realize we did that one numerically already, but I want to show you what it would look like if we evaluated this limit graphically. So I'm going to write A numerically, check, like we already did that one. Maybe I'll just write a little note here. C 2.1 basically it was this. Okay. All right, and we saw that it seemed like this limit approached 2. Let's go ahead and take a look at graphically. So what I'd like to do is go ahead and graph. I'm going to say f of x equals x squared minus 1 over x minus 1. What I'd like to do is graph this function. Okay, we can use our calculator for that. Everyone go ahead and take your calculators out because we'll be using them a lot today, both for doing the numerical and the graphical approach. Okay, I'm just making mine the dimensions I want. Okay, so what we're going to do is we're going to type this function in to our y equals and see what the graph looks like. So make sure that the x squared minus 1 and the x minus 1 are in parentheses. Enter. Looks good. Okay, I'm going to go to the graph. And this may or may not be surprising to you. What does it look like the graph is? Looks linear, doesn't it? Okay, that may seem surprising because this does not look like a linear function, does it? But we went through and we simplified it, didn't we, before? We said this is x minus 1, x plus 1. We canceled out the x minus 1s, and we were left with x plus 1. So notice this is a linear function. Remember that when we do this, we can do that as long as x is not 1. If x is 1, then we have 0 over 0, which we've established is not 1. Anything else is fine. So basically, if we were to graph this function, I'm going to go ahead and graph it here. And you can just use your calculator if you want, but it's nice to kind of have the... Well, there's something that your calculator's not showing, though. So right here at 1... actually, let me go ahead and zoom in a little bit, because we want to see what's going on near 1. So I'm going to go ahead and make this negative 1 to 2. And then it seemed like it was a pretty small window here. So let's go from maybe like negative 1 to 3 for our y. So negative 1 to 2 for the x, negative 1 to 3 for the y. And this just gives me a little bit better view of what's happening. Okay, so when I'm evaluating a limit graphically, what I'm looking for is, just like with the table of values, I'm trying to see as x gets closer and closer to 1, 1 is right here. As x gets closer and closer to 1, what does the y value seem to be approaching? And it can be a little tricky to see. This right here is 1, because I went from negative 1 to 3. So this is 1, 2. Doesn't it seem like it's approaching 2? Here, if I go kind of up, I'll try not to draw on my calculator. If I go kind of up and across, it looks like that y value is about 2. Let me go ahead and draw the graph, and I'll show you a little bit more of what I'm doing. So this is negative 1, 1, negative 1, 1. So we can just graph x plus 1. That has a y-intercept here at 1. It has a slope of 1. So it would be just this linear equation. I'm going to keep it going. But I'm not graphing x plus 1. I'm graphing x squared minus 1 over x minus 1, because that's the limit that I'm trying to find. So the difference between those two graphs is that this one is undefined at 1. F of 1 is undefined, because I get that 0 over 0 situation. So that means that there's going to be a hole at 1. Okay, so there's going to be a hole. If I keep going with this line, it's going to go this way. There's going to be a hole right here, because the function is undefined at 1, and then it's going to keep going. Okay, so this is the graph of f of x. So there's this hole right here. But, and I know, do you guys remember what a hole means? It means that the function value does not exist at that point. Okay? If I had a closed circle here, then that would mean the function value is 2 at that point. Or if I had a closed dot up here, it means that's the function value at that point. We'll go into more detail on that later. But the idea here is that as x approaches 1, it seems like the y value is approaching 2. So we can go ahead and say we've investigated this both numerically and graphically. We can go ahead and say that the limit is 2. We're not going to look at symbolically just yet. That's actually going to be in section 2.3. Okay, how are we feeling about this so far? We have questions? Okay. Yes, Haley. Mhm. Mhm. Yeah, so there is a domain restriction, right? So basically, like, the domain of this function is x cannot be 1, right? So it can be any other number except for 1. So that's actually what we're showing here in this graph by having that hole there. We're showing that 1 is not in the domain of that function. Does that answer your question? Yeah. I agree, yeah. So Nahaley said, but this expression, x plus 1, you can put anything into that, right? This domain is all real numbers, but this domain is x cannot be 1, which is why this little piece of info here is so important. Because we're saying that these are equal as long as x is not 1, and then they're no longer equal. So if you plug in 2 to this expression here, and you plug 2 into this expression, you'll get the exact same number. Let me just show you. 2 squared minus 1 would be 4 minus 1, which is 3. It would be 3 over 1, which is 3. 2 plus 1, also 3. So that'll work for every number except for 1, because at 1, this becomes 0 over 0, which is undefined. But at 1, this becomes 2, which is actually where the algebraic approach to evaluating these limits comes in. Because I can sometimes use algebra to get rid of a 0 over 0 situation, and then I can essentially, like, plug in the 1 value. Yeah. That's what we'll do in 2.3. Absolutely awesome questions. Okay, so let me do kind of a generalization here to this notation as far as when we're evaluating a limit graphically. So if you have the graph of a function, I'm again going to do kind of a boring function here, f of x. If we're finding the limit at a, that essentially means that we are trying to get x as close to a as possible from both directions, from both the right side and the left side. And we are looking at what the y value is approaching. This isn't always going to be f of a, okay? Because remember that when we're doing a limit, we're not saying that x is a, right? We're saying that x is getting ridiculously close to a, but not a, right? It's close, but not, it's never the same thing. They're just very close to each other. So as x approaches a, our function value is going to start to approach some number, which I'm going to go ahead and just call L, capital L, for limit. So this is just a little visual of what we'll see when we evaluate limits graphically. We're seeing as x approaches this point A, the input, the y value, f of x, is approaching some limit L. Okay, let's keep going. We need to do more examples. Okay, let's look at, I'll put that here just in case anyone needs to write that down more. B. Let's take a look at the limit as theta approaches 0 of sine theta divided by theta. Sorry, can't see that. The limit as theta approaches 0 of sine theta divided by theta. All right, so we're going to do this two ways. We're going to look at this numerically and graphically. And the graphical part, I probably don't know what that function looks like, so we're going to go ahead and use our calculator for this. Okay, let's start with the numerical part. That means that we are going to make a table of values where we get theta very close to 0 from both directions, from both the left and from the right. So I'm going to put theta as my first column, and then we're going to evaluate this expression, sine theta over theta, for different values of theta. Now, we want theta to get very close to 0, so someone give me a number that's close to 0. Sure. So 0.1, maybe we can start with that, and I think I heard some more extra zeros in there. Maybe we could do 0.01, 0.001. That seems fine. You could get closer if you want to, but you want to do as many values as you need to be able to get a picture of the overall limit, to be able to make an educated guess as to what the limit is. All right, this right now would be like if I graph this on a number line, here's 0, right? So right now these represent this side over here, right? So we would say this is from the right side, because all of these numbers are just to the right of the actual number 0, okay? When we're evaluating a limit, we need to have the big picture idea. We don't just want to know what's going on from one direction. We want to know what's going on from both directions. So we are going to put in numbers that are smaller than 0 also. So that would be like negative 0.1, negative 0.001, right? So what I usually like to do is I like my numbers to get smaller this way, and then I like them to approach upwards this way. So what I'm going to do is make this a negative 0.001, and then a negative 0.01, and a negative 0.1. So this is nice because then I can see my from the right is kind of approaching down this way. And then you see how this one would end up being from the left? From the left. That is going to approach, because these are getting closer and closer to 0 in an upward fashion, I guess. So these are from the left. Now there's one number that I'm not plugging in here, 0, right? Sometimes it can be informative to plug in 0, just to kind of see what's going to happen. Let's just do it mentally, just to see what happens. What is the sign of 0? Remember that trig review video I told you guys about? Or no, wait, did I tell you about that? I think I told my Calc 2 class about that. I'll post it for you guys. I have a trig review video that goes over the entire unit circle, how to find the radian measures, how to find the coordinates, sine, cosine, tangent. That's going to be so important in this class and in pretty much every other calculus class you take from this point on, and math, physics, all that stuff. So I'll post that in the news item, maybe during the break. So sine gives you, so here's the angle of 0. Sine gives you the y-coordinate on the unit circle. What is the y? Here's x, here's y. It's 0, isn't it? The y-coordinate at this point is 0. So I have in the numerator sine of, I'll write this out, at theta equals 0, sine theta over theta equals, sine of 0 is 0 over 0. You see how we get that indeterminate form? Okay, so that's one of the reasons why this numerical and graphical approach is very important. Okay, but again, we're not plugging in 0. That's not the idea. This just gives you an overall picture of like what's happening at that point. But in order to evaluate the limit, we need to plug in these numbers that are very close to 0. All right, let's do that. I know, I've been all talk so far. Time to spring into action. All right, make sure your calculator is in radian mode and not in degree mode. So if you go to mode, I am in degree mode right now because I taught 112 last term, so we were doing stuff in degrees. Pretty much we will never have our calculator in degree mode for this class or any other calc classes that I can think of. So pretty much just keep it in radian mode and you'll be good. All right, so we want to put in sine. Now I'm not going to put in sine of theta because your calculator always wants your input to be x. So I'm going to put sine of x divided by x, but I know that my variable in this particular case is theta. All right, and then if I go to my table, so just to remind you guys, in the table settings, you want to make sure that your independent is set on ask as opposed to auto, and that allows you to type in whatever things you want to for the input. Mine's already set there, so I'm going to go to the table. I'm going to clear out all this stuff that I don't need. If you have an 89, the way to clear it out is hit clear enter repeatedly until all of the things in the table are gone. Okay, here's what we want to plug in. 0.1, 0.01, 0.001, negative 0.001, negative 0.01, and negative 0.1. That'll be fine. Okay, now I know it feels tedious, but I recommend writing these y values into your notes so that when you look back later, you know exactly what your calculator gave you and where you came to your conclusion from. So I'm going to go ahead and do that. And I recommend rounding as far as you need to where none of the values are repeated. Like these all are going to all of these inputs are going to give different outputs, even though sometimes they look similar. Like, do you see how this right now my calculator says at 0.001 that the y value is 1. That's not true. It's not 1. If you hover over it, it's just rounding. If you hover over it, you'll see There's just a heck of a lot of 0.99s, and that's why it's writing it that way. So what I recommend doing for this one, this is our 0.1, I'm going to go ahead and go out 5 decimal places for this one, 0.99833. The next one, 0.999998. The next one was 0.999999. That's fine. All right, and then my next one was also 0.9999 and another 9. And it looks like these values are just going to get repeated again from the other side. 99998 and 99833. Okay. So it's looking like as my input theta is approaching 0 from both sides, that the expression seems to be approaching what number? Seems to be approaching 1. Okay, so I can go ahead and make an educated guess then that the limit as theta approaches 0 of sine theta over theta equals 1. Do I know for sure that it's exactly 1? No, but we're making a good guess about it. Later on, there is a way of proving, actually, that this is 1. It's kind of a cool geometric proof, but we won't dive into that just yet. Yeah, what's up? Oh, I'm really glad you asked that. So the question was, when you say equals 1, should we do like an approximate sign instead, right? Now, because of the way this notation is, so if I read this notation out loud, here's what it means. As theta approaches 0, or let me say it, start over. The limit as theta approaches 0 of sine theta over theta is 1. And that really means that as theta approaches 0, sine theta over theta approaches 1. So there's already kind of like an approximation kind of idea with this particular notation, even though we're using an equal sign. So I'm going to actually just write that real quick. This is also saying as theta approaches 0, sine theta over theta approaches 1, just in a more condensed way. Great question. Okay, I'd like to talk about one-sided limits now, okay, because we've kind of established this idea that these numbers that were just bigger than 0 were coming in from the right side, and these numbers that were just smaller than 0 were coming in from the left side. Okay, so one-sided limits, let's talk about that notation, and then I think we're probably getting about ready to take a little break. One-sided limits. Okay, so the idea here is that with one-sided limits, if I just want to approach something from one direction instead of from both directions, there's a way that we can notate that. So right-sided limit is going to have a very similar notation. I'm going to write this first, and then I'm going to edit it to make it the right side. Right now it's the limit as opposed to the right-sided limit. I'm going to add my changes in just a second. Okay. Nope, sorry, you can't even see it anyway. So, all right, so the right-sided limit means we would want to be plugging in numbers that are just bigger than a. And the way that we notate that is we put a superscript plus sign above the a. And that indicates that we are plugging in numbers that are bigger, plus, bigger than a. What do you guys think we use for the left side? A minus. So we're going to use a superscript minus sign to show that we are wanting to approach a from the left side. That is, plugging in numbers that are smaller than a. So up here, for example, I could say numerically that the limit as theta approaches 0 from the right, if I just look at the right side, I'm just going to be looking at these green parts here. So I basically would just completely ignore this part here. Okay, I'm doing this to cover up that table, but I'm also showing off my ring. So it seems like from the right side, as theta gets closer to 0, that sine theta over theta is approaching 1, isn't it? 0.99. And if you aren't sure, you can always add another 0 here, see what you end up getting for this. There would just be even more 9s. So we can say then the right-sided limit is 1. Similarly, actually let me make that green just so you know exactly where that came from. Similarly, the limit as theta approaches 0 from the left. Okay, I'm going to now cover up the stuff that was from the right. And we can see that from the left side, as theta gets closer to 0 from the left, our expression or our y values are also getting closer and closer to 1. Okay, so that's that side. Yes? Absolutely. Yeah, so we will get to a point where maybe we need to do more than this in order to establish what the limit is. And we might also get to a situation where the limit doesn't seem to be approaching any particular number. We'll have a few examples like that. So one thing I want to talk about with these one-sided limits is they're very important, especially when we talk about doing these graphically. But notice that in this particular case, the right-sided limit is 1 and the left-sided limit is 1. And do you see how the overall limit was also 1? So notice that this particular notation does not have a plus or a minus. When it does not have that, it means that we want to approach from both directions. And when we did that, we noticed that from both directions, it was approaching 1. So in order for a limit to exist, for the limit as x approaches a of f of x to exist, we must have the left-sided limit be equal to the right-sided limit. I'm going to write equals L, where L is a finite number. Sometimes we'll get to a situation where, and we'll do some more examples. Maybe I'll come back to this after we have done an example where we don't seem to be approaching a finite number. All right. It is 10 o'clock. You feeling like a little break is in order? Okay, so we've done this numerically. We talked about one-sided limits. Let's take a look at this limit graphically, and we'll see if we come to the same conclusion. Oh, why am I putting my phone here? I need the calculator. Here we go. Okay, let's go. I need to go back to my y equals because I put something else in here during the break. Okay, so, all right, let's take a look at the graph. Now, you would always want to adjust your window when you're evaluating these limits. Negative 10 to 10, negative 10 to 10 is rarely going to cut it, because we always want to get pretty close to a number, right? So we want to try to have a fairly narrow window around that number. In this particular case, we want our input to approach 0. So maybe like from negative 1 to 1, that would be sufficient. And then I don't know what your y should end up being, right? If you've done this numerically, you have an idea of what your y values are going to approach, so you could go ahead and go with that. I think probably from maybe negative 1 to 2 would give us a good window. I wouldn't want to just go up to 1 because it seems like the limit's going to be 1, so I want to make sure I can see above that also. And feel free to play around with your windows to get it how you want it. Okay, so here's my y-axis, which means that this is where x is 0. And I made my window from negative 1 to 2. So this is negative 1, 0, 1, 2. So I can see graphically that it looks like this limit is approaching 1. Now, one thing, again, that your calculator is not showing you is that if I let my function be, like let's say I say f of theta is sine theta over theta, f of 0 is undefined. Because again, it has that 0 over 0 situation. So your calculator is not going to show you holes, but a hole is right here because the function is undefined at 0. Sorry, I put theta. Oh, no, there we go. So if I were to graph this, I'm just going to do a rough sketch. I do kind of want to go out a little bit more because I want to show you this is kind of a cool graph. Let's go from maybe like negative 5 to 5 in our x scale. So this just gives you a little bit bigger of a picture. So we can see that it looks like, again, there's a hole right here that your calculator's not showing you. And that hole appears at 1. Okay? So we would say then that as theta approaches 0, this is our theta axis, our output is approaching 1. Do we all agree that f of 0 is not 1? Right? But that's not what this is. That's not what's being asked here. Oh, sorry, you guys. I still have this off. It's asking what the function is approaching as theta approaches 0. So as theta approaches 0, this approaches 1. Okay. All right. Let's take a look at a few more. I think I'm going to skip ahead a little bit here. Let's do. I think we can do 2 more. Yes. Yeah, well, potentially, like you've been graphing functions in your calculator and it hasn't been showing you holes that are there. But if you ever find the domain of a function, right? So we can see that if our function is sine theta over theta, that because division by 0 happens when theta is 0, then 0 would not be in the domain of this function. So that would tell us, like from the equation, that 0 is not in that domain. So there should either be like an asymptote at 0, or a hole at 0, or some sort of issue at 0. We will talk about that. Jumping ahead, Haley. Okay, let's do another one. Let's look at the limit as x approaches -2 of absolute value x plus 2 over x plus 2. Okay, so again, we're going to use our calculator. I'm going to go a little quicker through this one because we still have another section to talk about. So you might be wondering where the heck we can find an absolute value. So if you go to, actually I'm trying to remember. Yes, I think it's in math. So in on the 89, it's second 5. Yep, there it is. So second 5, if you have an 83, there should just be a math button. 83 or an 84 should just be a math button. And then under number, you should see absolute value, ABS. Okay, so we want the absolute value of x plus 2 divided by parentheses x plus 2. So we're going to make a table. X, absolute value x plus 2 over x plus 2. So we want to plug in numbers that are close to -2. Okay, we're going to want to approach from both sides. Okay, if you aren't quite sure how to approach that or how to begin doing this, a number line can be helpful, right? So this is -1, it'll be -3. So I'm going to start approaching from the right. So that would be numbers that are bigger than -2. So that would be like -1.9, -1.99. Put that over there for right now. -1.9, -1.99, -1.999. Okay, and then I want to approach from the left side as well. Left side being numbers that are just smaller than -2. So that would be like -2.001, -2.01, -2.1. I generally use 3 values from the right, 3 values from the left. I recommend that you use at least 2 values from the right and 2 values from the left. Definitely don't just do 1. It's not going to give you a picture of what you need. So I like 3, but you should do at least 2. All right, putting this into our calculator. All right, clear out what we have in the table here. All right, plugging in -1.9, -1.99, -1.999, -2.001, -2.01, -2.1. To do what? Oh, I just hit the down arrow. Not that I know of. Yeah, I know. The nice thing about if you have an 83 or an 84, as soon as you hit enter, it just goes right down to the next one, but not on this one. I can't tell you how many times I've started typing the next one, but I'm like going over the previous one. Yeah, so just hit that down arrow. Okay, so looking over at our y values, hey, this is interesting. 1, 1, 1. It's just 1. 1, 1, 1. And then from this side, I have -1, -1, -1. Interesting. Let's talk about a little bit about why that's happening. Let's do a little example. Like, let's say if I were to evaluate this at like 3, Just picking 3 as an example. Okay, that would be absolute value of 5 over 5. What is the absolute value of 5? 5, right? It's just whatever that, make that number positive, it's already positive. 1. So it can equal 1. Well, let's try maybe a different number, like negative 5. So I'd have absolute value negative 3 over negative 3. What's the absolute value of negative 3? Positive 3 divided by negative 3 gives me a negative 1. So basically, if the number that I pick is to the left of negative 2, I'm going to end up getting a negative 1. If I pick a number to the right of negative 2, I'm going to get a positive 1. The reason why that happens is because you see how if the number is smaller than negative 2, then this is going to be a negative number, right? And then that's going to be a negative, but if I take the absolute value, it becomes a positive. So I end up getting this, they'll be the exact same number, just one will be positive, one will be negative, producing a negative 1. Whereas if I go to the right of negative 2, this will be a positive number, its absolute value stays the same, and you just end up getting a positive 1. So basically, if I were to graph this function, here's negative 2, going from negative 1 to 1. So let's see. If I go to the right of, the right of negative 2, I'm going to see a positive 1 everywhere. If I go to the left of negative 2, I'm going to see a negative 1 everywhere. What about at negative 2? Maybe an asymptote? Well, what do I get when I plug in negative 2? I get a 0 on the bottom. What about on top? Absolute value of 0 is 0. So I get 0 over 0. I know, this keeps popping up, doesn't it? So indeterminate form. Now, there actually won't be an asymptote here. The reason why I know there's not going to be an asymptote is because the y values are not approaching a big number, right? Asymptotes mean that if you approach that number, negative 2, that your y values would just grow and grow and grow without bound. But I'm seeing that they stay consistent. They stay at 1 and they stay at negative 1. But this function is undefined at negative 2, isn't it? So the way that I'm going to denote that is I should have an open circle here and an open circle here to show that this function value is undefined at negative 2, but this is what's happening to the left of it, and this is what's happening to the right of it. So it seems like what's happening is that the limit as x approaches negative 2, if I approach from the left, this is where those one-sided limits are important. From the left, that's this part, right? So I approach from the left, what is this limit approaching? One, right? Oh, did I draw this incorrectly? Wait, hang on. Oh, wait, yeah, this is from the right. This is from the right, not from the left. Boop, from the right. Okay, from the right because negative 1.9, negative 1.99, those are over here. Those are to the right of negative 2. So my y values are approaching a positive 1. And then if I look at the left-sided limit, which would be these, that's approaching a negative 1. So I'm seeing this from the table. I am also seeing it from the graph, that as we approach these, as we approach negative 2, from the left we get a negative 1, from the right we get a positive 1. Now that gets back to what I had talked about when we did one-sided limits, that for a limit to exist, its left-sided limit and its right-sided limit must agree with one another. Do they agree in this case? They don't. One side's saying it's negative 1, the other side's going, no, it's positive 1. They don't agree, so we would say the limit then does not exist at this point. So we would say then that the limit as x approaches negative 2 of absolute value x plus 2 over x plus 2. Here's the way we would write that. We write equals dne. It means the limit does not exist. Thank you. So the limit does not exist. So notice the notation I used was different depending on the side that I was approaching. If I approach from the right, the limit is 1. If I approach from the left, the limit is -1, which means that the limit, remember this means I'm approaching from both directions. If those sided limits don't agree, then we say the limit does not exist. Yeah, we always use that D&E, does not exist. Yes? Yeah, so it depends on what the question was asking. If it just says evaluate this limit, you could go ahead and not write that and just say the limit doesn't exist, and that would be fine. If it said additionally, like explain why, or determine the one-sided limits and then state a conclusion or something like that, then I'd want to see all that. But you can pretty much never give me too much information, so more information is generally better. Okay, let's take a look at that. I want to do this graphically stuff real quick. So let's take a look at the graph that I handed out earlier, and then we're going to go into 2.3. We may have to go over into lab just a teeny bit. Hopefully not, though. We'll see. Okay, so in this case, we have no equation. All we have is a graph. Okay, so we're looking at the limit as x approaches 1 of this function. All we have is the graph, no equation. So just as a reminder, the open circles mean that the function value is not defined at that point. The closed circles mean that the function value is defined at that point. Okay, so the limit as x approaches 1 of this function. Okay, in this case, we're looking at limits, so we really don't care about what's happening at a point. We care about what's happening near a point. I'm going to write that here. We want to know what's happening near, not at. So if we look at as x approaches 1, that's right here, right? What does it seem like our y value is approaching? Right, as we approach 1 from the right or the left, my curve, my y value, is approaching 0, isn't it? So we would say then that the limit of this function at 1 is 0. All right, let's do some one-sided limits. As we approach -2 from the right. Okay, here's -2. Now this is where sometimes students get mixed up with the from the right, from the left. From the right just means consider like as if you were plugging in numbers bigger than -2. Okay, so here's -2. We would want to be going in from the right. And I realize that's a little confusing because technically that means we're moving left because we're coming from the right. Okay, just keep that in mind. We're coming from the right, which means we're going this direction. So what does it seem like our y values are approaching? -1. We come in here, the y value is approaching -1. All right, how about if we approach -2 from the left? Does not exist? Well, let's see. Are we thinking does not exist because of this open circle? Maybe -3? That's some controversy. Oh, but we got a closed circle here. So here's the question here. Do we care about what's happening at -2? No. We care about what's happening near -2. So this closed circle means absolutely nothing when we're talking about limits. Eventually we'll talk about continuity, and then it will come into play. But when we're talking about just limits, we don't care at all what's happening at that point. We care about what's happening near that point. So as x approaches -2 from the left, what does the y value approach? -3. So that is the limit. So this closed circle here could not be here at all, and that wouldn't change anything that we've written so far. Additionally, it could be an open circle here, and then I could fill it in up here, and that also would not change our answers at all from what we've done so far. Okay, our left-sided limit was -3, our right-sided limit was -1. So what is the limit as we approach -2? Does not exist. The left limit and the right limit aren't agreeing, so the limit does not exist. How are we doing so far? Good. Okay. The limit as x approaches 3. What do we think? Infinity? Yeah, maybe undefined. There's an asymptote there, isn't there? Okay. So we see this asymptote. So let's talk about, actually, let's do this left-sided limit first, and then we'll jump back over to this one here. So the left-sided limit. So notice that as we approach 3 from the left, our y values are going up to infinity, positive infinity, right? Just keep going up and up. Because of this vertical asymptote, they're approaching positive infinity. So technically that means that the limit does not exist, okay, because our y values are not approaching a single finite number. That gets back to that thing that I wrote earlier, where in order for the limit to exist, the left and the right limit need to be equal, and they need to be a finite number. Okay, so in this particular case, the limit does not exist. But do you see how it doesn't exist for a very different reason than this one did? Like, this one didn't exist because the left and the right didn't match each other, okay? But the left and the right existed, didn't they? In this particular situation, the left limit doesn't exist because the y values are approaching infinity. And rather than writing d and e, we're actually going to write infinity because it's more informative than just writing d and e. So I know that might seem kind of weird that we're saying that this limit is infinity. But remember that when we have this equal sign, we're still saying approaches. This is saying as x approaches 3 from the left, the y values, the function, is approaching infinity. So again, technically, this does not exist, but writing infinity is more informative. So anytime that your limit is approaching infinity, go ahead and just write infinity. Let me do another example real quick. I think it might answer your question. What if we had the limit as x approaches 3 from the right? Yeah, as we approach from the right, our y values are going down to negative infinity. So again, it's more informative rather than writing d and e for us to write negative infinity. Okay. So what do you guys think we would say then about the limit as x approaches 3? Does not exist. A few different reasons. One, the left-sided limit and the right-sided limit don't agree with one another. And also, the left-sided limit and the right-sided limit don't exist. So both of those reasons, this is d and e. Let me give you another little example. If we had a situation, I'll just draw, let's say this is at 3, where we had a vertical asymptote at 3, but both directions were going up to positive infinity. In this particular case, maybe I'll say this is g of x. Now the left-sided limit would be infinity, right? And the right-sided limit would be infinity. So technically this means that the limit does not exist because the left-sided and the right-sided limits don't exist. They are not approaching a finite number. Okay? But do you see how at least in this particular case the left-sided limit and the right-sided limit agree with one another? They both approach positive infinity. So for this particular one, what we would do is we would say this limit is infinity. Again, technically this means that the limit does not exist, but it's more informative for us to write infinity, because if I tell you this limit is infinity, you get a picture in your mind, don't you, of an asymptote. But if I say this limit doesn't exist, you might not know why. It could be a situation like this. It's hard to say. One other one that I want to do here is the limit. I don't know why I didn't have this one in the first place. The limit as x approaches 0. Okay, take a look at our graph. The limit as x approaches 0. What do we think? Does not exist. Any other thoughts? 1. Any other thoughts? What do you think, Chandler? You're thinking negative 2? Got 3 different possibilities here. Okay, I'm going to ask another leading question. Do we care what's happening at 0? No. We care about what's happening near 0. Now, if I approach 0 from the left, what do my y values approach? 1. If I approach 0 from the right, what do my y values approach? 1. So what's the limit? 1. I realize that it's not nice looking, right? There's an issue there, but because we don't care what's happening at 0, we only care what's happening near 0, and the left-sided limit and the right-sided limit agree with each other, then the limit exists and is that number that the sided limits are giving us. So that limit would end up being 1. Now, if I started asking f values, like f of 0 is negative 2, right? That's this point right here. F of negative 2 is what? Is negative 1. Okay? But in the case of limits, none of that really matters. Okay? So we will be talking more about, we'll talk about something called continuity next week, and then those will start to matter a little bit more. Okay, we need to move forward.